by trace of powers of the matrix. So these pKs are trace of m to the k. And the spectral invariance of the matrix, so it's indeed unitary invariant. And if you do that with finite size matrices, well, you have some relations. If you do P big enough, then you have the relation of the characteristic polynomial of the matrix annihilates the matrix. So there is some relations. But formally, when you want to study the limit when n goes to infinity, which will be our main focus, you may consider that these relations just disappear and you have P1, P2, P3, etc. So you have a free ring of unitarily invariant observables, and you would like to compute expectation value of those. So the first kind of models people started to be interested in was of this form. So you look at the probability measure, where here you have the Lebesgue measure on the entries on the independent entries of the matrix. And we add a Gaussian term. And you may have some higher order term, so trace of a function I'm going to denote T01 of m. And you want to normalize it. So everything here depends on n, but I'm going to drop this dependence very soon in the notation. And so this z is the partition function. And it should be chosen such that the integral of the d mu m over all Hermitian matrices is 1. And just for this integral IQ to exist, so z to be finite, you may need some assumptions on the t's, and I will come to that later. So here T01 as a function of one variable, we take it to be either a polynomial or a power series. With only start with T3, T4, etc. And then you evaluate this function on the matrix and you take the trace. That's what appears here. So by solving the matrix model, depending on where you come from and what is your motivation, it could mean many different things. In this lecture, it will mean being able to compute all moments of any observables which are UN invariant. So things of this form. Remember, the P's are these trace of powers of the matrices, and L1, Ln are positive integers. And there's a better way, which is adapted for the large N asymptotic analysis that we will be concerned with. There's a better way to encode this. It's used what I will call the endpoint correlators. So Wn, it depends on x1, xn. And this is the cumulant expectation value of the traces of the resolvent of the matrix. And n here is bigger than 1. So I need to explain what is this cumulant expectation value. So it's in general, if you have random variables, real valued or complex valued, the cumulant of the n tuple of those random variables a1, an is the derivative respect to parameters s1, etc., up to sn at s equals 0 of the log of the usual expectation value of exponential of the sum of si ai. And it contains the same information as the expectation value. If you do n equal 1, it's just a log derivative, so you recognize the expectation value of a. If you do n equal 2, it's the second order derivative of the log. So you may have expected value of the product, because when I expand the exponential and I keep the first order term in the a's, I will have this. But because it's the derivative of the log, you also have a term which is the product of the expectation value with a minus sign. And you can continue. So you don't lose any information. If you know all the endpoint correlators, you would know all of these moments. So there's two settings one considers to consider these correlation functions. Either you want to consider x1, xn as complex numbers. In that case, where since the matrix is Hermitian, its spectrum is real, so you have to put the axis outside the real axis, so for that to be well defined. Or you just want to consider x as formal variables going to infinity. And then you use the fact that 1 over x minus m as a formal series. When x goes to infinity, it's m to the k over xk plus 1. And this is how you retrieve the moments. So wn x1, xn, when you expand all the xi's to infinity simultaneously, is going to be the sum over the l's, positive integers, the cumulant expectation value of PL1 of m, PLN of m, so the trace of powers. And this is encoded in the coefficient of x1 to the L1 plus 1, xn to the Ln plus 1. And you see that here I didn't take a k or L equals 0. This is because when n is bigger or equal to 2, when you take the nth order cumulant of two of random variables, and one of these random variables has a deterministic part, like the one here, there would be any m, so it would be something deterministic, it would just disappear. The only place where it still occurs is for n equal 1, you just have the usual expectation value, so you get the expectation value of this 1 over x1 with the trace, so that's an n. And so it comes with an 1 over x1. So I didn't specify much. What do we assume on these t or on this measure? I just said the partition function should exist. It turns out there's two different settings which shouldn't be confused, in which one can make sense of this. First, there's a case of formal matrix models. Where you consider all the TLs which appear in this measure to be formal variables. So in that sense, this measure is a perturbation of the Gaussian measure, which is here. And everything you compute is a formal power series in the T's. But if you come from probability, in fact, it's a different problem you're interested in. So I need a name, so we'll call that convergent matrix models. We just want to say that d mu is a probability measure. So in particular, the T's must be real, but not only. For example, if I took a polynomial which was of even degree with a positive dominant coefficient, this exponential here, we will exponential of some positive constant times x times trace of m to the 2l, and that's not integrable. It's going to blow up when the matrix goes at infinity in some sense. So you need some assumption making the integral converge. So typically, you want that v of x, when x goes to plus or minus infinity, should goes to minus infinity faster than, so here for some reasons I'm not explaining, at minus 2 log x. And on purpose, I'm being a bit vague about what does faster mean, because I will say a little bit about convergent matrix models and what you need, but it will not be the main core of the lecture. So that's what you want to do in probability. And that's what, in fact, you want to do in combinatorics. And the two settings are totally deserve to be considered. And in general, you obtain a different answer. So both are the matter of rigorous discussions and rigorous arguments, but things can look a bit different. And this is, in fact, harder. Good. So I will start with formal matrix models, because here we understand a bit more what's...
Sorry,
yes.
there is a question. Yeah.
Alex. What is exactly the condition there that they are not equal, the formal and the convergent matrix model? Can you say that in one slogan? What is the important thing that makes them different?
The important thing is that in the convergent matrix model, so I would say not equal, maybe I should say when n goes to infinity. If you're interested in doing here asymptotics for large n, that's going to become clear afterwards if you've not seen it before. Then you would obtain coefficient of asymptotic expansion that a priori depend on the T's. In the formal matrix model, we will see there's automatically, there is a large n expansion in some way, but in fact, it's an equality in terms of formal power series. And I mean that you cannot extend the large n limit or the large n expansion and the formal expansion in the T's near zero without extra assumptions. So perhaps I can discuss that a bit better, what is failing tomorrow when I talk about how we solve loop equations.
Okay, thank you.
And this question, in fact, is somewhat important historically because very often mathematicians thought that arguments of physicists were unrigorous concerning matrix models. And to some extent, not for everything, but it's because they were talking about different things. Physicists were doing formal expansions, and that's totally rigorous to make it here. Everything is a formal power series. and then you compute the coefficient. But these reasonings don't get through automatically when you talk about convergent matrix model. So for formal matrix models, we say that we have a perturbation of the Gaussian measure. So the good thing about formal parameters is that you can expand everything out of the exponential as a formal power series. And whenever you integrate, now you integrate against this Gaussian measure. So that has moments to all order. So it's well defined. And moreover, you can prove that it's allowed to extend the integral and the series expansion in the t's of that exponential here, which would totally be wrong in the convergent setting a priori. So when you do perturbation of the Gaussian measure, that's what people do in quantum field theory. You have a technique of Feynman diagrams for that. So there's a Feynman diagram expansion. And it amounts to evaluate moments of a Gaussian measure on a matrix. And that can be done using the weak theorem. So here I'm going to assume that many of you are familiar somehow with this sort of combinatorics. So we'll just outline how it works. So since in this exponential here, apart from the Gaussian, you have this sum of traces of powers, this would correspond to the vertices of our Feynman diagrams. So whenever you see a trace of m to the k, so a matrix has two indices. So I have an incoming line here, and it has k legs. And each of the sides of the legs correspond to the row and the column index of the matrix. So there's one incoming, one outgoing. So this would be a factor mij, then you would have m, so maybe I want mji. And then because it's a trace, the next index here should be the same. And so on. So here you have I that goes here. So it comes in, it goes out. Here there is another index L. It comes in, it goes out, and so on. And you have to sum over all indices between 1 and big M. So it's a graphical way to depict trace of m to the k. And the weak theorem tells you when you want to compute the moment of that respect to the Gaussian measure, so you have many of these traces of mk, you have to take such a picture and you have to pair lines together. And the specific shape of the model of the Gaussian measure we have forces the pairing to preserve indices along lines with same orientation. Preserving indices. Okay. So the Feynman diagrams in this case, so it's where I'm making a jump, because here I'm assuming that you already know something. So these are maps. So maps, one way to define it is that you have a finite set of building blocks, which are, so either we say these sort of fat vertices, but even a better way to think of it is looking at the dual. And the dual of this fat vertex is a k-gon. And the k-gon, I can orient it because for example, I go around here, and so on. So it's an oriented k-gon. And then the rules that you take these building blocks and then you glue pairs of edges. And here I will do in the dual. So pairs of edges along with opposite orientation. So if I have one of these K gone, here I have another one. I could also decide, well, I have to pair this and this. And you exhaust all the building blocks and the size of the building blocks that you have. And what you obtain is a discretized surface. Made out of polygons. So these are the commutative objects we're going to, all observables are going to be summed over. And if we do Wn, the particular shape of the measure implies that it has the following form. So it's a sum over all G integers of WGNs, where these don't depend on big N. So that's the only place where the size of the matrix comes up is a global factor. And that's an identity of formal power series in the T's, which mean that, in fact, it's not a large N expansion. On the left-hand side, this is a formal power series in T. On the right-hand side, this is a formal power series in T. And I claim that if you look at the coefficient of a given monomial in the T's, there's only going to be finitely many terms that contribute to the right-hand side. So how many finitely many? That depends on the monomial. If you take a higher degree monomial, you have to take into account more terms, but each time it's a finite sum on the right-hand side. And the WGN is a sum over connected maps of genus G, since we have connected surfaces, and so they're made of many small blocks. They're connected, they're oriented. So we have a genus with N labeled and rooted faces. So this means that somewhere we have special polygons. There's a distinguished edge on it. That's the root. And then you have many others to form the map. So I can have something like this. I'm only going to draw a little piece of it. Okay, this. In fact, here I could have two sides of the same glued together. So that's one side and another, but they're glued together. So you have this identification. That's still a polygon, but self-glued. And so on, so as to form a closed surface. So all edges are paired. And this phase must have length L1, Ln for the distinguished one. And each of these maps come with a certain weight, which is the product over K of Tk times number of K-gons. Since I have T3, T4, T5, I could have triangles, quadrangles, pentagons, and so on. There's a factor which remembers the length. So it's coupled to the variable xi's. And then you may have some symmetry factor. So this is a standard combinatorics of matrix model, which is found, for example, in Brezin et 600, Parisi and Zuber. And the specific dependence in N was, in fact, dates back to an observation of 't Hooft in gauge theory. So why is this factor of N like this? I can try to quickly explain this. So WGN, WN first, it is this cumulant. So cumulant means that you only take the connected diagrams. There's a relation between moments where you would have all maps. When you take the cumulants, you have all connected maps. These PL1, PL, and M, they create for you special vertices or faces like this. So that's the one which are in color here. And then you have the expansion of the measure, all these factors. So when you expand the exponential, you give yourself arbitrarily many building blocks, so polygons with various valency. And each of them come with a factor of N. So counting N, we have at least the number of faces which are not labeled, so the black one. Then you have a factor from the weak theorem coming from the pairing. That's given by the covariance of this Gaussian law. And because you have a factor of N here, you would get a 1 over N. That's the propagator. So you should get minus the number of edges. And then we have one thing more, which is that along each of those lines is circulating some index. And each time we have a trace, so we're really summing over all those indices, provided they preserve the long lines. So each of these index runs independently between 1 and big N. And when I look at the map, so this index is here, but when I connect, so here I have my dual, which was like this. So this index is coming here, is going here, then it's going all around the vertices of the dual. So for each vertex in the map, we must have a factor of N coming from these N different values of the index. And here, when we have a connected map, we recognize the Euler characteristic. It must be 2 minus 2G. But I remove the faces which are not labeled, and there's N of them, so it's 2 minus 2G minus N. And this explains this factor. So for this reason, also I said it's not a large N expansion, it's really an identity of formal power series. What we saw here is what one calls a topological expansion. Because at the end, the weight only dependence in N only depends on the topology. In particular, if we sort out by powers of N, we just extract maps of a given topology. And here, this identity, so here somehow there's nothing to prove. It's automatic that you have such a decomposition. Good. And that may not be guaranteed if you do convergent matrix models. The Wn, which is a function of big N, which is an integer, you would say, well, I want to look at the large N asymptotic expansion, and this may not always take this form. That's a big difference. So let's complicate a bit the thing, because then we can handle more interesting questions. So it's the multi-trace matrix models. So I want to write the most general UN invariant measure. So it should more or less only involve these power sum, powers of trace of powers, sorry, which has topological expansion. So it's d mu m. There's a normalization. You have the Gaussian measure. And here I'm just putting any series with some power n to the 2 minus 2h minus k, trace of thk of m1 mk. So thk is a function first of k variables. You could take that again as a polynomial or as a power series. So there's some coefficient th L1 Lk over L1 Lk for normalization, and then x1 L1 xk Lk. You assume these are symmetric. And then by mi, I mean that you take the identity matrix except at the ith position in a tensor product where you put the matrix M. And in total, there should be n tensor factors, k tensor factors. Therefore, if you make the trace of thk m1 mk, this will be the sum over L1 Lk positive, the coefficients. And here you would have trace of this product of matrices, but you see since they live in different tensor factor, when you take the trace, it amounts to take the trace, the product of the trace of the powers. So this is the compact way to write that you have a linear combination of product of traces of powers. Hence the name multi-trace matrix model.
Yeah, there is a question, Gaetan, so let's just
Yes.
Mike. Yeah.
So the determinant is also unitary invariant. Can you also have the determinant as an interaction?
Determinant is exponential of trace of log.
Okay.
So apart from what exactly convergence property has for these things, this is general.
Okay, yeah.
Determinant is okay? Or?
So determinant M is exponential trace of log M. So of course, log M doesn't have a series expansion at 0. But I want to see things still as a series expansion. So what I can say, I can just say, well, I don't do trace M, I do trace M plus C. And then I can expand in series when M goes to 0. Trace of sum over K. So there's a log of C. Minus 1 L over L. Trace of M to the L over C to the L. Plus 1. So if you allow me for series here with a certain finite degree of convergence, determinant fits. So here, if you want to do the Feynman diagram expansion, you get something that we call stuffed maps. It's not very different from before. We have building blocks. So the building blocks, they come really from what is beyond the Gaussian in the measure. Before, we just had trace of m to the k. So that was a single fat vertex of valency k, or a face, a k gone. But now we have product of traces. So you should think of these building blocks as k gons, which are together. So being together, more or less, you can say that, well, it's as if you had a certain surface, and I will put a genus H for the one coming from here. And this has a certain length L1, L2, Lk. And now that's your building blocks. So it's not anymore little disks, which are like polygons. It's pieces of surfaces with some genus and some number of boundaries. And so it stands together. There's nothing in between, just a piece that stands together. And then which you glue along pairs of edges in all possible ways with opposite orientation. So now a map. So let me try to draw one little example. So here is a boundary face. So if I want to see a term that will be computed in W1 of x. So W1 of x is a boundary with a certain length. And then we have some k gone, but we can also have, for example, a piece like this. That's a cylinder, so it's some building block with two boundaries. So if this has, so this has a weight T5, 1, 2, 3, 4, 5. Here, maybe I cut them like this. So that will have a weight T0 because cylinder has genus 0. And here's the length 1, 2, 3, 4, 5 for the first one, and then 1, 2 for the second one. And then you can continue. You could imagine that you have here a pair of pens. And then you continue to glue things. So we'll be interested in this kind of things. So I would say maybe I can already state the goal is, can one compute WGN? Or what does it take to compute WGN for all GN, which in this context of formal matrix model means computing, generating series of maps or stuffed maps with a fixed number of boundary and fixed genus. So I focus so far on the case of unitary invariant observables. But I want to stress the connection with free probability, where in fact you're interested in other types of observables. In some non-unitary invariant observables, but for still a UN invariant measure. So let's take gamma be a cycle of between 1 and n, so it could have smaller lengths. For example, 1, 3, 5 goes back to 1. And I'm going to define P gamma of m to be the product of the matrix entries using the structure of the cycle to take the matrix entry. So I do, if in the cycle M1 1 goes to 3 goes to 5, I'm going to take the product M1 3 times M3 5 times M5 1. So imagine I take some positive integers and I assume that n is big enough. You can take gamma I and gamma 1, gamma n to be pairwise disjoint cycles. Of length L1, Ln. And consider the cumulative expectation value of this cyclic product so many of these cyclic products, but the cycles are disjoint. And by UN invariance of the measure for which you take the expectation value, this is independent of which cycle you choose. It only depends on the length. So it's very similar to what we had before, except that now these things, it's not trace of powers. You really use certain matrix entry, so it's not going to be unitary invariant. And you may wonder what's the combinatorics behind that. So for this, we come back to our, how did we get the combinatorics for trace of power? We just say, well, trace of m to the k, it was this product of m with a certain cyclic order. So these indices were circulating like this. And I was summing over all the i's. Now it's a bit different in the sense that you don't sum over indices. The indices are really fixed. So for example, you have index 1 here, index 2 here, index 3, and you don't sum over that. So when you compute such an expectation value, these are faces, so blocks that you fix, which are there, they are labeled from 1 to n. So in the dual, this is, so here I have actually 5, so I should draw a pentagon. So that's the 1, 2, 3, 4. Sorry. The indices are more in the corners. 5. And then maybe you had another of these pieces because you look at a cumulant of order n. So that's the first one that has length L1. That has length L2. And because the cycles are disjoint, here I cannot have the same numbers. So when I glue my map, the gluing rules are the same. It's again moments of the Gaussian measure. What you see is that you will never be able to pair an index like this to an index like that. So this thing is a sum of what we call fully simple maps. So the same as before, but with a fully simple restriction. And fully simple mean that a vertex on a labeled face is incident to exactly 2 edges along this labeled face. So forbidden is to do this and to pair these two. So that would be something like this. And here this vertex has valency 3. So there's 3 edges of that face which are meeting here, so it's not allowed. You cannot either have something like this. Of course, you have other faces, so that, and they can do whatever they want. They can be self-glued. But these label 1, they cannot. So for example, this vertex here has 1, 2, 3, 1, 2, 3 again, edges on labeled faces, whichever labeled face, which are incident to it, and that's not allowed. So it's a constraint on maps. So if I want to speak about map without constraint, I'm call them ordinary. And the other one with these constraints that only concern the labeled faces, I call them fully simple. So it's a result that, in fact, there's also a nice way to encode these moments in a matrix observable. If you compute the expectation value of exponential of n trace of MA, A being a fixed Hermitian matrix, then you're going to see the exponential. And the generating series essentially of all these observables. So there's a power of n, you have 1 over n factorial. Then you're going to have this cumulative expectation value of p gamma 1, p gamma nm, where it is understood that here this is a cycle, this is a set of pairwise disjoint cycles with these lengths divided by L1 and n. And here, well, you still have to need the dependence in this matrix A. It's a function of A. So here you have PL1 of A. So the trace of powers of A. And so this up to normalization.
Gaetan, there is a question here. Yeah.
Yes.
So this is exactly the generalized Kontsevich model you're talking now with this external matrix A?
Not exactly. It's the, so you just take this kind of term. So in the Kontsevich model, there's several ways to see it, but sometimes the coupling is not linear between the M and the A. Here, I really want a linear coupling.
Okay. But I mean the generalized Kontsevich model. I mean the Kontsevich model has m to the 3, and then you can bring it in this form. And in the R spin matrix models, you have exactly this type of model, right?
You have some generalization of Kontsevich model that are of this type, indeed, but not all of them. And so this is known under the general name of matrix model with external field.
Okay.
External field being A.
Oh yeah, there is a question, Jamie.
Mingo. So Gaetan, the
Yeah.
Li is the number of elements in the cycle gamma I.
Yes.
I see. And when you take P, the polynomial in A, it's the same power as Li?
Yes, it's the same.
I see. Because I mean, in free probability, there's this formula of the convolution where you take something on one side and the Crevasse complement on the other side, because those matrices are asymptotically free, and even at finite level, if you generalize this. And but usually you don't get the same things on each side. I mean, here you've got the same powers on each side.
So here I'm saying that if you want to, some of you can say, I want to define a generating series. And then it has a nice expression as being this expectation body. I'm not saying more than that.
Yeah,
For the-
okay, no, it's just that the formula, I mean, I never thought about this exact thing, so I can't say, but that's what wouldn't have been what I've expected from the free probability version, but I'll check it later. Thanks.
So there are several ways to see this formula. One, with just an idea what is involved, is that because you have a UN invariant measure, even though the observables is not UN invariant, you can project on UN invariant observables by writing that whenever you have, I mean, for any function of M, this is also integral over against the harm measure. Maybe I put here an E of F of U mu dagger, just because U mu dagger is distributed in the same way as M by assumption. And then if F was, for example, this cyclic product of entries of the matrix, you're going to see, well, some powers of N and some powers of U. So you have to compute moments of entries of a unitary matrix, which is hard distributed. And that can be done by Van Gaetan calculus. So you manage to express the EC in terms of the usual, I can put the C or not the C, it's a general level, in terms of this, of trace of powers. But of course, I mean, a given L, given length here is going to involve many different Ks. And the relation, if you do Van Gaetan calculus, or there's also a combinatorial way to see that, goes by monotone Hurwitz numbers. And it's also known, that goes from the work, goes back to the work of Gaetan, Golden. And here, I don't know if John is in the audience. I'm sorry, I don't remember if it was Jackson or Jonathan Novak. Do you know? Yeah. Thank you.
It's a Novak. Yeah.
Yeah, I have a blank. I had a blank. Sorry. And so they prove that monotone Hurwitz number is what you get when you look at these type of integrals of a unitary group. So A and B are fixed. So it's called the Itzigson-Zuber Harish-Kandra integral. So I'm not going to define this, but when you compare the two, essentially you find this formula. Good. So what's the relation with free probability? Well, of course, in free probability, you're not so much interested into the formal matrix model. You do want actual random matrices, so the convergent matrix models. But what we learned from the formal matrix model, even though I told you it's not the same, that maybe in some good cases, you can hope that this Wn, these nth order cumulants, they're going to be of order, or the maximal order you can get when n, big N goes to infinity is n, big N to the 2 minus n. So it's a natural assumption to take. So here now, this is convergent matrix models. That Wn behaves like this at leading order. So then you can prove, it's automatic, that if you look at these expectation value of cyclic products, it's going to behave like the same thing, but minus a correction by the length of the cycles. Essentially because before you were doing trace of powers, so you were having exactly sum of Li indices that were running from 1 to n. And now you fixed all those indices to some fixed value. So you lost a factor of n. So the leading order is much smaller. And here there's some KL1, Ln, the leading order. So that's encoded in nth order cumulants. And if you compare to the theory of higher order free probability, so by Collins, Mingo, Speicher, and Schniadin, in fact, you find that these KL1, Ln are the nth order free cumulants. And then, of course, I could say a side question, which I won't have the time to discuss at all in these lectures, is not only, can you compute as well these free cumulants? And maybe go beyond leading order. So that I will not really talk about. Okay. So how much time is remaining? I have an impression that actually the time is almost over.
I think the time is up. So if you want,
okay,
yeah.
I'm going to wrap up by saying, so if I have 2 minutes to wrap up, is
Yeah,
it
yeah,
okay?
that's fine. That's fine. Absolutely fine. No problem. Yeah. Sure.
So some examples of matrix models. So there's a case where THK is 0 unless HK is 0, 1 or 0, 2. That means either you have n trace of m to the k, linear combination of those, or trace of m to the k1 times trace of m to the k2. In terms of maps, it means that you have only, so you have polygons plus cylinders. That's an important subcase where things actually will turn out to be simpler. So if I want to, the upshot is that that is WGN when they exist are given by topological recursion. In general, you don't have topological recursion, you have something which we call blob topological recursion, which you may already have heard in some talks, especially by Alexander. But you may wonder why at all would we consider these multi-trace matrix models? So the first thing is if you look at the two matrix model. So you have d mu1 m1, d mu2 m2. And imagine you couple them with, so still a quadratic term, so a trace of m1, m2. Now imagine I want to integrate, I'm only interested in two observables that only involve m1, so I can integrate over m2. But then I recognize my matrix model with external field, the external field being m1. So this is a new measure in M1. We have here the Z hat M1, and what is Z hat? It's exactly this, Z hat A. Well, to define this expectation value, I use the measure for the second matrix. So even though you started with d mu M1, which was only generating maps, you would actually get all these terms which contain multi-traces and to all orders, which in fact are generating series of maps of type 2 only with polygons of type 2, which are fully simple. So the combinatorics behind that is stuffed maps, where the building blocks are polygons of type 1, and fully simple maps, so something quite complicated a priori, of type 2. The two other examples, so are colored tensor, certain colored tensor models, which come up in higher dimensional discrete version of manifolds. So not two-dimensional like matrix model, but tensor models. So here there's some work of Bonhomme and D'Artois, and then several others afterwards, where indeed certain colored tensor models take actually the form effectively of these multi-trace matrix models. And then you can apply blob topological recursion to study them. And more recently, there's random spectral triples. So here by Shahbaz Arfa and Masoud Khalkhali, where certain natural model of random spectral triple again take the form of a multi-trace matrix model, where you only have finitely many of these TH. So it's a polynomial in the trace of powers, or the series truncate. And so this is some of the reason why I was asked to give these lectures, because the techniques that I'm going to explain for this multi-trace matrix model, and maybe a bit with more details for this case, but which extend to the fully general multi-trace matrix model, you can essentially use them in this kind of, to treat this kind of examples.
Okay.
I will stop here for today.
Okay. Thank you very much, Gaetan, for a great lecture. Let's thank Gaetan. Are there any questions? I mean, further questions? Yes, Alex.
Hi, it's Alex again. So you say the fully simple maps naturally appear in the two matrix model.
Mm-hmm.
Can you prove just with the two matrix model this XY symmetry between ordinary and fully simple maps? So you need really the ciliated maps?
Yes. So what I said here, it's a combinatorial identity, which is true, that you can see, and even you can prove that combinatorially. You look at a map in a two matrix model. So you have polygons of two types, 1 and 2. So you can think of it as the Ising model. And polygons of type 1 and 2 can touch each other. There's a certain ways for that. Type 1 can touch each other, type 2 the different ways, and then type 1, type 2 as well. So if you want to look at observables only involving M1, that amounts to look at maps of the Ising model, where the boundary is purely of type 1. But then you could say, well, okay, as soon as I see type 2 polygons, I'm going to cluster them together. So that could be small chunks, just an isolated type 2 polygon, or a big chunk. And this big chunk, you just take it out. And then you would like to say, well, I have now a map only with polygons of type 1 with holes in it. And in this hole, I have to glue the chunks of type 2. However, because of when you cut around these polygons of type 2, so you separate the chunks, if you want to glue back, so to have a combinatorial bijection, you in fact need that the boundary of type 2 along which you're going to glue is fully simple. If you have a boundary which is with self-gluing and another boundary with self-gluing, you cannot glue them together necessarily. So what works well at the bijective level is gluing ordinary boundaries to fully simple boundaries. And so this is why you have, I mean, that's where the word stuff is coming. That you see that you have your maps of type 1, but some pieces are actually these fully simple maps of type 2, which you put inside. So this identity, you could say then, okay, you know that two matrix models satisfy blob topological recursion. But in fact, something more is true, that for the formal two matrix model, it satisfies actual topological recursion. Yeah. And that you cannot see with this approach, or with what I'm going to say today. There's only one proof, which is a technical tour de force by Hénin and Orentin. It's just manipulating the loop equation in a complicated way, and then you manage to prove topological recursion. And so it cannot be used, I would say, to prove any effective topological recursion for the two matrix model. It's more a structural result, which here I mentioned more for illustrating the combinatorics behind that, also saying that most of the things that you say at the general level, I mean, to say this combinatorics, it's not really sensitive to which measure you do. In the same way that these free cumulants, that's true for any kind of measure, not only for the simple trace measure. So I wanted to illustrate this and say which kind of combinatorics is behind. But I cannot say I have any effective way to use that to say something about TR for the two matrix model, especially about the XY symmetry.
Okay, thank you.
Okay, any other questions here in the audience? There is something in the chat. Yeah, we'll get to that later, but in person people here, anything? Okay, so there is something in the chat. Do you want to?
Yeah, it's asking for references.
Yeah, you can. Oh, so this is for references. Okay, so very good. Yeah.
Yes. There are, I would say that there's not a standard, I would say, textbook. Well, okay, there's a book Counting Surfaces by Bertrand Hénard, yes, which is treating the one matrix model and the two matrix model. It takes a perspective of formal matrix models, and then you can consider things rigorously. And so yes, it's explaining the content of this. For this multi-trace matrix model, I wouldn't say there's not really a survey so far that exists, but there's some articles which I can forward.
Right. There is also this.
Okay, yeah. Thank you.
Okay, great. There is also this short memoir by Berzan, I think. Oh, he left. Huh? No. Oh, you see that? Oh, okay, very good. So anyhow, any other comments or questions? Okay, it seems there are none. So let's thank Gaetan again for great lectures. Yeah.
Thank you.
Okay, so we come back at 2 for El Glaser? Yes. For El Glaser lecture. Yeah. Very good. Thank you, Gaetan. Bye.
Bye.
Have a good evening. Yeah.